Okay, so continuing our discussion of rotational kinematics, I'm going to talk about where the rotational kinematics equations come from. So we can think of having cylindrical coordinates here where we've got r, theta, and z as our coordinate system. And if we have simple rotational motion of a rigid body that's only undergoing rotational motion and is not translating, then theta is the only part of this that is a function of time. Okay, and if we have kinematics, what that means is that d theta of d theta of t dt is omega, which is also a function of time, and then d omega dt t is alpha. This is constant. Okay, that's what we mean by kinematics. And so let's take this and see what other results we can get out of it. So if we start with this equation and integrate both sides, right, then we have our first kinematic equation. We're going to find that omega is omega naught plus alpha times t minus t naught. I should have written t's here. All right, because our alpha is a constant, so the integration of that is just alpha times t. And then we can think of this as that omega is alpha t plus some constant, and we want to set our constant such that at time t naught omega naught, omega equals omega naught. So that's where this equation comes from. We can then integrate this one again to get a function in terms of theta. So here on the left we'll have theta, a function of time, and then we're going to find that this is omega naught t minus t naught 1/2 alpha t minus t naught squared. Again, we can think of this as actually finding omega naught t plus 1/2 alpha t squared plus some constant, and then we're going to set our constant such that, I don't know where this VHS thing came from. Oops. We're going to set our constant such that at time t equals t naught, theta equals theta naught, and the way to do that is by putting everything in terms of these constants shown here, right? And then our last kinematic equation eliminates, for our last rotational kinematic equation is eliminate t. So substitute in our omega equals omega naught plus alpha t minus t naught into the theta equation. So if we solve for t minus t naught, so t minus t naught is omega minus omega naught over alpha. And then if we substitute that in for t naught above, then we will have theta equals theta naught plus omega times omega minus omega naught over alpha plus 1/2 alpha omega minus omega naught over alpha squared, and we can rearrange that to get our last kinematic equation. So I'm not going to show the details of this algebra here, but this would be the result. And all this derivation should look very familiar. It's very similar to how we derived the linear kinematic equations before. Okie doke.